Okay, so a couple videos ago, we looked at a ball accelerating near the surface of the Earth without air resistance, and the Earth is a little bit heavier, and we sort of talked about Riemann sums. And so then what I want to look at here is a ball that's being dropped and accelerating up to terminal velocity. Now, I could have sort of made things a little bit more difficult by putting in the constants that would sort of make it more realistic, but I opted in this video to make my model much simpler. So I'm saying that the terminal velocity is 1, and its initial acceleration is -1, and basically its coefficient of drag, all that stuff, they're all just 1. So basically it starts off, and so this is the graph of right now this is the graph of velocity versus time. Velocity versus time. And now we want to go backwards to okay, we want to go backwards to find the function that this is the derivative of. So this velocity versus time graph is the derivative of some function. Well, so let's see if we can figure this out. We have to use y again, so I can't sort of use the proper notation. I suppose I probably can, but I can't use the proper notation to do what I want to do. So we have to say, what gives you a derivative of 1? Well, what gives me a derivative of 1? X gives me a derivative of 1. This is a little bit harder. This is going to be, what gives me a derivative of -e to the -x? I'm going to get, it's going to be positive e to the -x. So if I take the derivative of this, derivative of x is 1. By chain rule, the derivative of e to the -x is going to be -e to the -x. So that should give me the distance of that should give me my distance. Now this comes into the whole thing of when you take the antiderivative, because the derivative of this, the derivative of x plus e to the -x is 1 minus e to the -x. But so is that's also going to give me the same derivative. This is also going to give me the same derivative. And in this case, this is what I want, because I want to say that my initial position, I'm dropping the ball, so I want to say that my initial position is 0, and so it starts at 0, and then it accelerates away from me. But then you see that as the velocity gets constant, then my distance versus time graph jumping around. If I sort of pull out here, my velocity is constant, and so my distance versus time graph is going to be a straight line with a constant slope equal to the velocity. So down here, down here, I've sort of initially got a quadratic equation as it accelerates, but then as it stops accelerating, it just straightens out. Okay, then as long as I've got it here, I want to find my acceleration graph. So, so pink is velocity versus time. Red is distance versus time. Blue is acceleration versus time. Okay, so then I say, well, what's the derivative of my velocity graph? So what's the derivative of 1? It's 0. What's the derivative of negative e to the negative x? It's going to be positive e to the negative x. So my acceleration is e to the negative x. And so this gives you sort of all the things that we were talking about before all comes back. And then I'm going to extend it here in just a second. So basically I start off, let's take all of these and just do the, let's just do from 0 to infinity. Okay, so we're cutting off everything we're cutting off all the negative numbers. So what I'm saying is that this object is going to start with an acceleration. This object starts with an acceleration of 1 and an initial velocity of 0 and an initial position of 0. As it accelerates, the velocity goes up, and as the velocity goes up, it encounters more air resistance. So as it encounters more air resistance, the acceleration goes down. Acceleration is the curvature. So acceleration is the second derivative of the red. So as the curvature, the second derivative or the curvature goes down, the red straightens out. So where the acceleration or the second derivative is at its maximum, the red has the most curvature. As the acceleration dips down to 0, the red straightens out, has less curvature. And so then this, the pink, gives me the slope of that line, slope of the red line. So here the slope is 0, and so the red line is more or less horizontal. As the slope increases, the red line bends up, but then as the slope becomes constant, then the red line straightens out at a constant slope. Okay, so that's again a recap to derivatives, and now we're going to sort of look at numerical integration, because it's sort of a real powerful thing. This is sort of a fundamental theorem thing. I'm going to take the integral from 0 to 1 of my velocity function. So I'm going to take my velocity function and I'm going to plug it in. And so what this is saying again is it's saying Take the velocity function and plug in 0. Multiply that, so that gets me my initial velocity. Multiply that by a really small number dx. Now move over, plug dx into the velocity function, and see what you get, and multiply that by dx. Move over by dx, keep repeating until you get up to 1. Then add up the area of all those tiny little boxes. And the computer, when it does it, it comes up with 0.367879. Now, if I find the y value of the red function, so the red is my derivative, the red function is my integral, it's my antiderivative. So this is the integral. I find that the value of the red function is, you probably can't see it there, but that says right there 0.367879. Well, what happens if I tell my computer to go to 2.3? From 0 to 2.3. Well, it goes and it adds up. Let me do this. I want to add one. I'm going to make it pink. And we're going to say 0 is less than or equal to y is less than or equal to this function. Add this in. And we're going from 0 to 2.3. So what I just told the calculator to do in this expression here is I said, basically, find the pink area. So divide this pink area into a series of vertical boxes with a height f of x and a width dx. Add up all the little areas and tell me what you get. And this says that it gets 1.4026. 1.40026. Now if I go on the red function and I go right there, again the font is too small for you to see, but here's 1.5. Right there it says 1.40026. So the red function is the antiderivative of the purple function, or the pink function if you want to call it that. And the red function tells you the area under the pink function. So the value of the red function is the cumulative area under the pink function. So that's something more for you to chew on, and that's where I'm going to end this video.